Welcome back, everybody. Today, we're going to be taking a deep dive into something pretty fascinating in the world of large language models. You know, those powerful AIs that are out there generating text, translating languages, and even writing code these days.
Yes, and the development we'll be exploring today really centers around how we train these LLMs, specifically a technique called layer normalization, which basically ensures smooth information processing across all those many layers of a model.
Okay, so it's like making sure all the different parts of the AI are sort of working together smoothly.
Exactly. For a while now, researchers have mainly been using two main types of layer normalization, pre-LN and post-LN. But recently, there's been a bit of a wrench thrown in the works. Turns out the deepest layers in these really complex LLMs, despite all the computational power that goes into them, often don't contribute as much as they could to the overall model's performance.
Oh, wow. So it's like building this huge complex machine and then finding out like a whole section of it isn't really doing anything.
It is, and that really raises the question, why are these layers even there if they're not really pulling their weight? The research paper we're diving into today tries to tackle this head on, and it's titled Mix-LN, Unleashing the Power of Deeper Layers by Combining Pre-LN and Post-LN.
Interesting. Okay, so MixLN, from what I'm gathering here, is this new approach to layer normalization. And it's really aiming to make those deeper layers useful, right?
And that's the core idea. But to really understand how it works, we have to grasp why the traditional methods, pre-LN and post-LN, have these limitations. Let's imagine the information flowing through an LLM as a signal, like traveling along a complex pathway.
Okay, so I'm picturing a signal, like a pulse of energy kind of moving through the network.
Now, with pre-LN, that signal, it starts off strong, but it weakens as it travels deeper. It's like it's losing energy along the way, so those deeper layers aren't really getting a strong enough signal to learn effectively.
Okay, so those layers are kind of like starved for information in a way.
Precisely. Now, on the other hand, with post-LN, the signal is strong in the deeper layers, but it's weak in the early ones. It's almost like the signal is blocked early on, so those initial layers aren't getting what they need to begin with.
So it seems like both methods have their own downsides. So then where does this MixLN come in?
Well, Mix-LN combines the best of both worlds, really. It combines pre-LN and post-LN, but strategically. It applies post-LN to the early layers to give a strong signal at the very beginning, and then it switches to pre-LN for the deeper layers.
So it's sort of clearing the path for the signal at the start, and then it's amplifying it as it goes deeper.
That's a good way to put it. This balanced approach really makes sure that the signal or that information flows smoothly and effectively through the entire network, letting all those layers contribute to the learning process.
That's a really neat solution. But the real question is, does it actually work in practice? What kind of results did the researchers actually see when they tried out this MixLN approach?
Well, the results are pretty compelling, actually. They tested Mix-LN on a whole bunch of different LLM sizes and consistently found that it outperformed both pre-LN and post-LN. One of the key metrics they were looking at is perplexity, which essentially measures how well the model predicts the next word in a sequence.
So lower perplexity basically means the model is doing a better job at understanding language and generating it.
Exactly. What they found was that Mix-LN was achieving significantly lower perplexity scores compared to the other methods, and this happened regardless of how big the model was. For example, on a model with 71 million parameters, Mix-LN achieved a perplexity of 33.12 compared to 34.77 for pre-LN.
That's impressive. Even what seems like a small difference in perplexity can actually lead to some pretty noticeable improvements in a model's fluency and how coherent it is.
Absolutely. But the cool thing is, the benefits of Mix-LN go beyond these perplexity spheres. It also seems to improve the model's overall ability to learn.
Okay, I'm all ears. How does MixLN impact that learning process?
They tested Mix-LN in a couple key areas. Supervised fine-tuning, which is where you train the model for very specific tasks, and reinforcement learning from human feedback, also called RLHF. And in both areas, Mix-LN were showing some remarkable gains compared to traditional methods. For instance, with supervised fine-tuning, they saw an average improvement of 4.26% for a 250 million parameter model.
Wow, those are some serious gains. So MixLN is not only making those deeper layers useful, it's actually making the entire model a more efficient and effective learner.
That's the key takeaway, really. Now, the question becomes, why is Mix-LN so effective? What's actually happening under the hood that's allowing it to achieve these kind of results?
That's what I want to know. Is it just that the information is flowing more smoothly, or is there something else going on?
Well, it's a combination of factors. Like we've talked about, MixLN definitely ensures that information flows in a balanced way throughout the network. But it also seems to be promoting something called representation diversity.
Okay, representation diversity. What does that mean when we're talking about LLMs?
Basically, it means the different layers of the model are learning to specialize in different aspects of the information they're processing. So instead of all layers learning very similar things, MixLN actually encourages them to develop their own unique perspectives, almost like areas of expertise.
So it's almost like having a whole team of specialists, each with their own skills and knowledge, all working together to solve a problem, right?
That's a really great analogy. And this diversity of knowledge, this representation diversity, it seems to be really crucial for building these more robust, more nuanced AI models. It's almost like having a model with a much wider range of perspectives so it can understand and respond to a much wider range of situations.
This is really fascinating, but how did the researchers actually measure this representation diversity? And it's not like you can just look inside the model and see what each layer is thinking.
Right, it's not that straightforward. They actually used a couple of pretty clever techniques to assess what individual layers were contributing and see how MixLN was impacting how those layers were learning.
Okay, I'm interested to hear about these techniques. What did they do to sort of peek inside the black box of these LLMs?
One technique they used is called angular distance, and it's basically a way to measure how similar or different the representations that are learned by different layers are.
Angular distance. That sounds like something out of geometry class. How does that even apply to AI?
I know, right? It's a bit technical, but basically what they're doing is measuring the angle between the representations learned by different layers. Imagine plotting the representations of each layer as points in some high-dimensional space. If two layers are learning really similar things, their points would be pretty close together. So that means there's a small angular distance between them. But if they're learning very different, diverse things, their points are going to be farther apart. And that results in a larger angular distance.
Okay, so the greater the angular distance, the more diverse the knowledge, and the better the model's overall understanding.
Exactly. And what they found was that MixLN actually led to much greater angular distances between layers compared to something like pre-LN, especially in those deeper layers. So that gives some pretty strong evidence that MixLN is really promoting greater representation diversity.
That's a pretty compelling finding. It really sounds like MixLN is shaking things up in a big way. But angular distance wasn't the only technique they used, was it? There was another method they used to evaluate individual layers.
Yes. They also use a technique called performance drop. It involves systematically removing individual layers from the model and then measuring how much the overall performance decreases.
Okay, I'm getting the picture.
Yeah.
So by removing different layers and seeing how much the performance drops, they could figure out which layers were really meaningfully contributing to the model's understanding, right?
Exactly. And what they found was pretty interesting. With pre-LN, removing those deeper layers barely made a difference in the performance. But with mix-LN, removing those same deeper layers actually caused a noticeable drop in accuracy.
So it's like MixLN is actually turning these previously ignored, underutilized layers into essential parts of how the AI learns. It's pretty remarkable, isn't it? How even just a small change in the training can make such a huge difference in how the model learns and understands.
It really highlights how interconnected these complex systems are, and how even just subtle adjustments can ripple through the entire network and change how it behaves.
This is all really exciting stuff, but let's take a step back for a moment and just let this all sink in. We've covered a lot of ground here, and I want to make sure we're all on the same page.
Yes, it's definitely important to pause and really think about the key takeaways.
So for all of you listening out there, what are your initial thoughts on this whole MixLN thing? What's jumping out at you so far?
Really take a moment to think about what this new approach to training LLMs could mean.
All right, we'll be right back to continue this exploration of MixLN and delve even deeper into its potential impact on the future of AI.
Welcome back. I hope that gave you a chance to, digest everything about MixLN. It's pretty exciting stuff, isn't it?
Oh, yeah, for sure. It's like we've been throwing all this computing power, all these resources at building these huge models. And now MixLN is showing us that we can actually get way more out of them if we just train them in a smarter way.
That's a great point, and it really brings us to some broader implications of this whole discovery.
Mm.
What does the success of MixLN tell us about the future of, AI development in general?
Right. Where could this lead?
Well, one immediate implication is that we could see significantly faster and more efficient training for LLMs. Remember all those deeper layers we were talking about, the ones that were essentially wasted resources?
Yeah, it was like having a whole section of the factory that was just sitting there idle.
Exactly. Now with MixLN, we're finally utilizing the full capacity of these models, which means we could potentially achieve the same performance, but with smaller models. Or, we could even unlock even higher levels of performance with the same computational resources we're using now.
So it's not just about making these models bigger and bigger, it's about making the models we have smarter and more efficient.
Exactly. And this has huge implications for the cost of AI development, even its accessibility. Imagine a future where, even smaller research teams or startups could train really powerful LLMs. This could lead to a much wider range of applications and innovations that we haven't even thought of yet.
That's a really cool thought. It could really democratize this powerful tech and lead to a whole new wave of AI-driven solutions.
Yeah.
And it's not just about speed and efficiency, right? There's also this potential for more robust AI systems thanks to that representation diversity that we talked about.
Absolutely. A model that has this diverse set of representations is going to be much less likely to be thrown off by something unexpected, inputs or weird scenarios. It's like having a team of experts with totally different perspectives, which, leads to better decision making overall.
So it's not just making the models faster or more accurate. It's about making them more intelligent in a way,
Yeah,
more adaptable and capable of dealing with the real world.
that's it. And that's going to be really important if we want to build AI systems that we can really trust and rely on for all sorts of things, even critical tasks.
It all sounds very promising, but were there any limitations mentioned in the paper or challenges they ran into? I mean, no scientific breakthrough is perfect,
Hmm.
right? There are always things to improve on.
You're absolutely right. You always have to be cautious. The researchers did point out a couple of areas where, future research is needed.
Hmm.
While MixLN showed great results across those different model sizes, they did note that the optimal point to switch between post-LN and pre-LN, it might actually vary. It could depend on the model's architecture or the specific task you're trying to do.
So it's not really a one-size-fits-all solution. It's more like a flexible framework that you can sort of adapt and fine-tune depending on what you need it for.
That's a good way to think about it. It's like a powerful tool, but you can customize it. And that's part of what makes it so exciting, really. It opens up a whole new area of research to explore, like all the nuances of MixLN and how to optimize it for all sorts of different use cases.
It definitely seems like we're just scratching the surface of what's possible with this technique.
Yeah.
It makes me wonder what other, seemingly small tweaks or adjustments we could make in AI development that could lead to huge breakthroughs.
That's a great question. And it's this kind of thinking, this willingness to challenge how we do things and explore new approaches that really drives innovation in AI.
And speaking of new
Yeah.
approaches, I was really intrigued by the fact that they didn't just test this MixLN on language models. They actually tried it out on, what are they called? Vision transformers? VITs.
That was a really cool part of the paper. It suggests that these benefits of MixLN, they might actually extend beyond just language processing and into other areas of AI, like computer vision.
Wow. It's like discovering this fundamental principle that applies to many different types of AI.
Exactly. And they actually saw performance gains when they applied MixLN to VITs, which are used for things like image recognition and object detection. So this really hints at the possibility that MixLN could be this more general principle for improving how we train all sorts of neural networks.
That's a pretty big deal. It's like finding a key that can unlock potential in all these different AI systems. So this is what I love about AI research. There's always something new and exciting just around the corner.
It's constantly evolving, for sure. And this MixLN research really shows the power of human creativity and ingenuity to keep pushing the boundaries of what's possible.
It really makes you wonder what other hidden potential is out there just waiting to be discovered. What other seemingly insignificant tweaks or insights could lead to the next big breakthrough in AI?
It's a great question to ponder, and it really highlights how important it is to foster this culture of curiosity and experimentation in AI research. We need to encourage researchers to think outside the box, to really challenge the status quo and explore these unconventional ideas.
Absolutely. And, we've covered a lot of ground today. We've really explored the what, the why, and the how of MixLN. We've talked about its potential impact on the future of AI. And we even touched on its implications for other fields, like computer vision.
It's been a fascinating journey for sure, going through the complexities of this breakthrough, and I really hope that our listeners are feeling as inspired as I am by the possibilities that MixLN is presenting us with.
I know I am. But before we wrap things up entirely, I think it's important to bring it back to our listeners and give them a moment to really reflect on everything we've talked about.
You're right. Let's summarize the key takeaways from this discussion.
So, for those of you listening, what are your main takeaways from our deep dive into MixLN so far? What are you thinking about its potential impact on AI as a whole?
Take a moment to really consider how this tweak, this change to layer normalization, could really revolutionize how we approach training and developing AI.
Okay. We'll be right back in just a moment to finish up our deep dive into MixLN and leave you with a few final thoughts. Okay, so let's jump back into this whole MixLN thing.
Yeah.
It's amazing to me how even the tiniest tweaks can lead to such big changes, in these complex systems. It makes me think, how did these researchers even discover and prove that MixLN is so effective?
Well, they were very systematic about it, actually. They designed their experiments really carefully so they could isolate the effects of MixLN and compare it to other methods. They didn't just assume it would work, they actually put it to the test.
So they had to rigorously test it against those, I guess you could call them those reigning champions of layer normalization, like the pre-LN and the post-LN.
Yeah, exactly. And they didn't just test it on one model either. They wanted to see how MixLN performed across a whole range of LLM sizes. So, they started with smaller models with like 71 million parameters, and then they went all the way up to much larger models with billions of parameters. That way they could figure out if the benefits of MixLN actually got better as the models got more complex.
Well, that's smart. It's like testing a new engine on a bunch of different vehicles. From like a compact car all the way up to a huge truck. You want to make sure it works across the board, right?
Yeah, exactly. And what they found was really cool. The results were consistent across all those different model sizes. So no matter the size, MixLN always outperformed the other techniques. They got lower perplexity scores, and it really showed how MixLN could unlock the power of all those deeper layers.
That is super impressive. But I'm curious, how did they actually measure the impact of MixLN on all those individual layers? It's not like you can just, open up the model and watch what each layer is doing.
You're right. It's not that easy. They had to get a little creative with how they measured things. One of the things they used was something called angular distance.
Okay, you're going to have to explain this one to me. Angular distance sounds a little intimidating.
I know, right? But think of it this way. Each layer in the model is learning, a representation of the info it's processing. We can think of these representations as like points in this multidimensional space. So the angular distance between two layers is basically a measure of how different those representations are.
So if two layers are learning really similar stuff, their representations would be close together, so that's a small angular distance.
Exactly. But if two layers are learning different things, specialized knowledge, then their representations would be farther apart. And that means a larger angular distance.
Ah, okay. So the greater the angular distance between those layers, the more diversity there is in the knowledge, and the better the model understands things overall.
You got it. And the cool thing is, the researchers found that MixLN consistently led to these larger angular distances between layers compared to the other methods, especially in the deeper layers. And this was some pretty good evidence that MixLN was actually promoting greater representation diversity, which, like we talked about, is really important for building those more robust and adaptable AI systems.
Yeah, it's like MixLN is encouraging each layer to become its own little expert, right?
Right.
Creating a whole team of these specialized learners inside the model.
That's a great way to put it. But they didn't just stop there. They also used another technique called performance drop to make sure what they were seeing was accurate.
Performance drop. What's that all about?
It's a pretty simple but effective idea. They just systematically removed individual layers from the model and measured how much the performance dropped. This let them see which layers were super important for accuracy and which ones were, less important.
Oh, so like with a car, you remove different parts one by one to see which ones are absolutely necessary and which ones, you could maybe do without.
Exactly. And what they found with MixLN was super interesting. When they removed the deeper layers, the ones that were kind of underutilized before, it actually led to a noticeable drop in performance.
Wow, so MixLN wasn't just making the deeper layers more active, it was making them crucial to how the model was understanding things.
Exactly. And that really reinforces the idea that MixLN is unlocking all this power in the deeper layers, changing them from being sort of passive bystanders to these active parts of how the model is learning.
It's crazy to think that a small change in the training can have such a big impact. on how these models actually learn and understand the world.
It definitely shows how complex and interconnected these AI systems are. We're just scratching the surface of what they can do. And discoveries like this, MixLN, are opening up the door for, even more powerful and sophisticated AI in the future.
Well, as we wrap up our deep dive into MixLN, I want to thank all of you listeners for coming along with us on this exploration. We hope you've learned a lot about this breakthrough and what it means for the future of AI.
It's been great to, untangle all the complexities of MixLN with all of you. And as always, keep exploring, keep asking questions, keep learning. There's a whole world of amazing discoveries waiting to be found in the world of AI.
That's right. Until next time, stay curious, everyone.